In digital communications, we are concerned with the transmission of one of the M messages generated by an information source. This message gets transmitted by using one of the M message signals or waveforms. Now, at the receiver, what we receive is basically a noisy version of this message signal. The goal of the receiver is basically to detect which one of the M message signal was transmitted in the presence of noise. Now, this signal detection problem and determination of the optimum receiver gets simplified if we could represent signals in terms of vectors. Now, if we assume the additive noise model of the channel, then your received signal is equal to the message signal plus the noise signal. Now, we know that given a set of message signals, we can always generate a complete orthonormal basis signals for this set. So, I can represent each of the message signals in terms of a vector. So, now if you could represent the noise signal also in terms of vectors, then our detection problem will get simplified. Okay. So, now we start our study with Emery communication in the presence of additive white Gaussian noise, and the first thing we do is basically to look at the vector representation of a random process. Fine. So, let us consider a complete orthonormal set of basis signals phi k t for a signal space defined over the interval a b, correct. Then any deterministic signal st in this signal space will satisfy the following condition. Where your Sk is the projection of St over the basis signal phi k t. This is also denoted as follows. Now, this implies that for any t in the interval between a and b, we have the equality St is equal to now for random processes defined over the interval a to b, this statement is generally not true. So, we require certain modifications, and let us see what are those. So, our goal is now to determine basis function for a random process or basis signals Okay. So, first of all, a general random process xt cannot strictly satisfy the following equation. correct. Instead, a proper convergence requirement is in the mean square sense. What it means that it satisfies this equation. Now, this equality can be denoted as xt is equal to xk phi k t over all k, but this is equality in the mean square sense. So, if you have two random processes xt and yt, and if we say that these two random processes are equal in the mean square sense, then practically the difference between xt and yt random processes have zero energy, correct. So, as far as we are concerned in communications, signals or signal differences with zero energy have no physical effect and can be considered to be 0. Okay. For set of deterministic signals, the basis signals can be derived via the Gram-Schmidt orthogonal procedure, which we have studied earlier, correct. However, Gram-Schmidt procedure is invalid for random processes, correct. A random process is an ensemble of signals. The basis signals for this random process will depend on the characteristic of the random process. There are many ways in which a random process can be expanded in terms of a sequence of random variables and orthonormal basis phi kt. Now, if we require the additional condition that the random variable xk be mutually uncorrelated, then the orthonormal basis have to be solution of an eigenfunction problem given by an integral equation whose kernel is the autocovariance function of the random process, and it will be given as follows. So, in this your autocovariance function Cx T1 comma T2 is by definition autocorrelation function minus the means . So, where your means are defined as follows. This is the expectation of the random process xt, correct. This is the autocorrelation of the random process . And this is a kernel function in this equation, correct. So, solving this integral equation results in the orthonormal basis phi k t, and projecting the random process on this basis results in the sequence of uncorrelated random variables x k. Okay. So, here this function, once you get, you have to normalize it properly. So, this condition is satisfied, and then the KL expansion this is known as Kahrun-Loo or KL expansion, and it is given as follows. Okay. So, this equality is in the mean square sense. It is important to note that, please. Okay. So, now if your random process has 0 mean, correct, then you could substitute the auto-covariance function by autocorrelation function, and then it would be something like this. So, these are known as eigenvalues and this is known as eigenfunction. So, in this case basically this autocorrelation function becomes your kernel function, correct. Now, what it says basically that given a random process and if you desire the coefficients of expansions which are going to be random variables to be uncorrelated, then this basis functions basically are obtained by solution of this integral equation. That means this basis function cannot be selected arbitrarily, correct, and depending on the random process obtaining this basis function, orthonormal basis function may not be a very trivial task. Okay. So, let us consider one special case of this random process, and we will consider for that matter to be stationary white noise. So, we will determine the basis signals for stationary white noise process. Okay. So, we know that for a stationary white noise process, let me assume the white noise process to be NT, I am considering noise, so I am writing as NT, and the autocorrelation for this, because it is a white noise and is stationary, what it implies is that since the noise is white, its power spectral density will be flat. So, autocorrelation will be an impulse. Okay. So, for this spatial kernel, the integral equation, this will reduce to the simple form as follows. Now, using the property of an impulse, this is easily shown to be equal to n by 2 phi k t, t belonging to the interval a b, correct. So, what this implies that any complete orthonormal set of basis signals can be used to represent the stationary white noise process, correct. And additionally, all the eigenvalues are identical and lambda k is equal to italic n by 2, a very important result. Okay. Now, let us consider this white noise process to be having 0 mean, correct. So, if that is the condition, then let us look at the expansion of this white noise process in terms of the basis signals. So, as we have said, we could use any complete orthonormal basis signal set, and I will be able to represent my noise process Nt as N1 phi 1 t plus N2 phi 2 t plus, right. So, this is summation of it is important to note that this N1, N2 are random variables, because this is a random process which consists of ensembles, and we are taking the projection of that onto this phi 1 2, phi 1 t, phi 2 3 and all that. So, depending on a given sample function from this random process, you will get different coefficients of expansions. So, what it means basically, each coefficient of expansion is going to be a random variable, correct. So, it is important to note that when you write this as a random process, then this is a random variable, but if I write it as a sample function of this noise process, then this I should write it as N1 phi 1 t plus N2 phi 2 t, and this will be the summations like this. Fine. So, please note this difference between a random process and the sample function of the random process. So, now if we assume that our Nt is a 0 mean random process, let us look at the properties of this random variables Nk, which is nothing but the projection of the noise process onto the basis signals. Fine. So, we take the average of this random variable, this will be equal to average of this quantity I can change the order Now, this quantity is equal to 0 because we assume it to be 0 mean random process. So, it means basically this is equal to 0, fine, okay. Now, let us look at the covariance of two random variables nk and nj. So, I am interested in finding out the covariance of nk and nj. Okay. So, we will write this as this is by definition equal to this. Now, we are assuming a 0 mean process and also a stationary process, correct. So, this will reduce to just this quantity, this will go to 0, okay. And this I can write it as follows. So, this is the projection I will get nk, nj I will get the projection of nt, sorry we will use this phi j l dl, correct. So, this I can write by changing the order as follows. Now, assuming that your noise is white, then I can substitute this by an impulse. So, this I can write it as it is a white stationary noise. This can be simplified as this will be equal to phi k when t equal to L only, then this value will be existing. So, what this implies is this will be equal to italic n by 2 when k is equal to j is equal to 0 when k is not equal to j by the property of the orthonormal set, correct. So, what this shows is basically that I get my random variables nk and j to be uncorrelated, correct. So, and the variance of each of these random variable turns out to be italic n by 2, correct. So, now if this noise process was a Gaussian, then my Nk, Nj would also be Gaussian random variables. In that case, when Gaussian random variables are uncorrelated, it will also imply that they are independent, correct. So, for a white stationary Gaussian noise, it will imply independence of Nk and Nj random variables. Okay. Now, having studied this, we will see basically how to incorporate this idea of vector representation of a noise process into a design of an optimum receiver for Emery communication in additive white Gaussian noise scenario, and we will continue this study in the next class. Thank you.